Hello everyone and welcome back to my channel XYZ Architect. I'm Marius and today we are going to talk about datum systems. And because this is a complex subject, we will have more parts and more videos for this subject. So as you asked, and without losing any more time, let's get right to it. Datum system. When a geometrical characteristics have to fit between certain technical specification in order to see the form deviation, its position or orientation, it has to be done in reference with a theoretical exact feature, named datum. The datum feature is represented by a real element that belongs to the part and has a low form deviation. The ideal element of the nominal element is the same feature but with perfect form associated to the real element. And we can see here the representation. Okay, so this is the representation from the drawing. We have the tolerance frame right here. We have the nominal surface, right? So this is the nominal surface from the drawing. And derived nominal characteristic, which is a line for this cylinder. And right here we have the real surface. At number 5 we have the extracted surface. Then we associate the surface, the measured surface, to the nominal surface, and the derived element of the associated feature is still an axis. And this is the datum reference. This will be the datum reference for the cylinder, the measured cylinder. Datum indicators. So as we see here in the left side, we will see exactly how a datum is represented on a technical drawing. Okay, so you can see it like this, you can see it like this, you can see it also like this. So keep this in mind. This is not the only way that you can see the datum represented on the drawing, but we will talk about other representation in the following videos. Okay, let's see the first example. So, as we see here in the right side, we have different example where the tolerance element is a dimensional characteristic and the datum is the axis or the symmetry plane. So, for example, here it's the axis of the cylinder and the datum is put on the extension of the quotation line. So it's clearly it will be here on the center. Here we also have it, but it's represented in another way. So for example, here we can have a true position or we can have a concentricity or something for the cylinder, but it's also a datum. This can also be a common datum, so it will be represented as A minus B, so keep this in mind also. Here also it's the center of the circle, and here also it's the center of the circle, and here it's the center plane from these two surfaces. Okay, so let's see an example of this done on the GOM. For the first example, where the alignment is the dimensional characteristic and the datum is the axis or the symmetry plane, we will use the drawing of the part from the GOM, where datum F is a symmetry plane, as we can see on the drawing. Okay, so as we see here, datum F is a symmetry plane. So the way we do this is go to construction, plane, fitting plane, then we take a plane on the left side, take a plane on the right side. Okay, rename them in order for us to work organized. We will rename plane 1 F1 and plane 2 F2. so we can know that it constructs datum F. Okay, we check them both, set the measuring principle to reference construction, and now we can construct a symmetric plane from these two. F1, F2, create, and again measuring principle, reference construction, and we can rename this to datum F. And now we have datum F. So this is the way we can make a symmetry plane datum. Okay, so now that we have datum F, we can evaluate this symmetry. Let's see how we can do this. Okay, so we make again a plane, fitting plane right here, another one right here. Okay, we put now the measuring principle as fitting element. Best fit 3 sigma. Okay, good. And now we can construct again a median plane, a symmetric plane from plane 1 and plane 2. Create and close. Fitting element, automatic. Let's rename this as symmetry plane 1. Okay, let's go to inspection, check GD&T, symmetry of symmetry plane 1 for datum F with a tolerance of 0.8, exactly as the drawing specifies. And we can see now that we have a deviation, so the dimension is not okay. We have an actual 0.88, so we have a deviation of 0.08 above the tolerance. For our second example, the datum is a feature that is not a dimensional characteristic. It's on the indicated surface. For example, it can be represented like this, it can be represented like this. Also, this is correct from this side. This is very important. Keep an eye out for this, because this can be confusing. Or you can do a mistake and think this, oh okay, so this is the hole and the datum is a hole, but no, it's not a hole, it's the surface next to the hole. So keep this in mind, and let's see an example on the GOM for this one also. For the second example, where the elements are not a dimensional characteristic and the datum is the indicated surface, we have from this drawing datum D and datum E. So let's make them on the GOM inspect suite. Okay, let's construct a plane, fitting plane. Let's call this datum D. Let's make it as a best fit for now, and let's take this datum E and close it. Put the measuring principle as reference construction, and now we have datum D and datum E, plane elements where the drawing indicates exactly on the surface. So as we see here and here. Okay, so now let's try to make the two positions from here, because it's in regards to datum D and E, but I think we have to make a datum system, datum D and datum E. Yep. Okay. Yes, it's fine. Okay, good. So let's create it. We have now datum D and E, and let's construct a cylinder. Okay, create and close. Measuring principal fitting element. Okay, good. And now let's evaluate the GD&T position. Datum system D and E. I think it's a circular. Yes, it's a circular, and it has to have 35 on this direction and 145 on this direction. Okay, so as we see here, 145 on the x-axis and 35 on the y-axis. So we can see this is the x-axis and this is the y-axis. Okay, and we have 0.5, right? 0.5, yeah. Good. No material requirements as ISO 1101 specifies, or we can have the ASME Y14.5, but it's the same. And as we can see here also we have a big deviation of 1.33 millimeters. So it's a very big deviation. It's 0.83 millimeter deviations above the tolerance. And the last one, the case where with a single datum with partial surface coverage. Okay, so it's not that common. You will not see this on every drawing, but you can see them on some of them, where the datum is just a partial surface of the plane, for example, as we see here. So it's indicated that we have to go from here, from this plane, 10 millimeters, and from 10 millimeters from this plane, search 23 millimeters and do the datums only on a surface of 23 millimeters from this plane. Okay, good. Let's move on. Construction of a reference frame to a specific reference system. So datums are constructed generally from geometrical elements of exact form, like points, lines, planes, and so on. These elements coexist in the interior of a frame constructed from three mutual perpendicular planes that intersect one another, known as reference system. As we see here, we have three planes, right? So the first plane, for example, can be the bottom plane. The second plane can be the lateral from the left side plane, and the third plane can be this front plane. Notice that the angle between them is 90 degrees, as we can see here, because this is a typical alignment, the typical reference system. Okay, we can also see the normal of the plane, the measurement direction of the plane. So if we touch, for example, a plane here, right here, 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 and here, the normal of the plane will be like this, as we see here, upwards. And for this one, in this side and for this one in this side, if we touch it like this and this one like this. Okay, we also can see the rotation here, the rotation from the intersection line from all of the three planes, and this is the datum point origin. So this is the point where the origin of the system will be. So XYZ origin will be right here in this point. Okay, so we can see here the reference frame from the drawing. This will be from the drawing, and we can see that it has a primary datum, a secondary datum, and a tertiary datum. So when you see something like this, please keep in mind that this is the way that you have to construct the alignment. The first datum will have to be A, the secondary datum will have to be B, and the tertiary datum will have to be C. So when we will have all of the datums, all the primary, the secondary, and the tertiary datum, we will take all degrees of freedom from the part. There are 6 degrees of freedom from the part, as we talked in previous videos, as maybe you remember. So it's 3 translations and 3 rotations. That makes 6 degrees. Okay, so in order to construct a complete datum system, we will use datum A, we will use datum B, and instead of doing datum C as it specifies here, we will do datum C on the big plane from here. Actually, we will do datum A on the big plane, datum B here, and datum C here. I see datum A doing datum A here, taking a large surface and doing a more stable alignment. So let's do it like this. Okay, again, plane, fitting plane. Let's take this. Okay, call it datum A. Okay, let's take this one, call it datum B, and let's take this one and call it datum C. Now that we have all 3 of them, let's make it reference construction for all of them. Takes a little time in order for the program to evaluate them. Okay, and now we can go and make a local a datum system. Let's put datum A on the primary datum, and as we see here, it remains 2 translations and 1 rotation. So datum A took 2 rotations and 1 translation. Okay, good. Datum B will take the other rotation and 1 translation, so it will took the translation from here and the rotation from here, so the part will not move like this anymore. Datum A took the rotation from here, so the part will not rotate like this. Okay, and neither like this. So like this, right? And like this. And now datum B, it took the rotation like this. This took this rotation. And the translation, obviously A took the translation from the Z-axis and B took the rotation from the Y-axis. and the only thing then that remains is the translation on the x-axis, which will be took by datum C. And now we have three perpendicular planes intersected by each other, and here we have the origin. Good. So let's see also an example of taking the degrees of freedom from the part. The example is this one right here. We have a clamp and we have a support for the clamp, and the clamp is being assembled on the support by welding. So the designer think about the reference system, taking in consideration the role of each surface that touches the counterpart. So the clamp sits on the support with the straight surface datum A right here, right as we see here, having the biggest extension of the surface on the support. So when it comes in contact with the support, it comes with the biggest surface datum A on the support right there. What this does, it takes 3 degrees of freedom from the clamp. The rotation on AB and CA axis. Okay, so AB, so the clamp will not be able to rotate on the AB axis, and also will not be able to rotate on the CA axis. Okay, and it will take also the translation on the BC axis. BC axis is this one, right? BC axis. So it will not be able to translate on the BC axis anymore. The second reference, datum B, is set on the side with the biggest length. So on the side with the biggest length right here, this side. So the clamp will move on datum A on this plane until it touches datum B, until it touches this plane right here. Okay, what this does, it takes 2 degrees of freedom from the part, the rotation on the BC axis. Okay, so the rotation on the BC axis is taken right now, and so the clamp will not be able to rotate like this anymore, right? So on the BC, just imagine this as an axis on the 3D, and imagine that the clamp will not be able to rotate like this anymore on this axis, right? Okay, and it will take also the translation on CA axis. So this is CA axis, and the translation will be taken from this axis. The part will not be able to move on this axis anymore. Now the clamp can only move on the AB axis, so it can only move like this. So in order to take this movement, the last reference is taken with the side where datum C is indicated, so this side right here, moving the clamp along the AB axis until it touches datum C, so this plane right here. So now the last degree of freedom from the part is taken, and the part is not able to move anymore in any direction, and it's not able to rotate anymore in any direction. So, hope you like this first part. There will be more videos on this subject, as I said in the intro, and I will reach probably 100 subscribers in the future very soon, and I would like to thank the community for this. This means a lot to me. Thank you guys so much, because we are a small community. 100 people watching what I'm doing means a lot to me. So I would like to thank you all for the involvement that you have on this channel, and I will like to thank you for everything, and I really hope that my videos inspire you, and I hope my videos help you in your day-to-day work and everything. So yeah, thank you so much, and see you again next time.